Warning, the video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, Professor of Mathematics at Cosumnes River College in Sacramento, California. This video is a continuation of the quotient and product rules in derivatives for Calc 1, and we've just proven the product rule and used the product rule in a few examples. Now we're going to introduce ourselves to the more complex rule, which is the quotient rule, and we're also going to prove it. Now I have to be honest with you, I've never bothered proving this rule, but I kind of scratched it out before this video, and I think I really like how this proof works, so I'm going to go ahead and do the proof here. The quotient rule is kind of an awkward rule. Remember, the product rule told us that the derivative with respect to x, or maybe I should just write it in Lagrange notation, the derivative of the product of f and g is f prime g plus fg prime, and I write it in that order every single time. Well, the quotient rule tells us that if you have two differentiable functions, f and g, then the derivative of their quotient is going to be f prime g minus, so it starts the same way, f prime g, but minus, instead of plus, fg prime, all over g squared. Again, in Lagrange notation, it's this right here. The derivative of f over g is f prime g minus fg prime over g squared. Notice the order in which it's written in the numerator matches the order in which I always teach the product rule. So just remember f prime first, f prime g, and then if it's a quotient, minus fg prime. If it's a product, plus fg prime. And the quotient has g squared in the denominator. The proof of this, as I scratched it out, is almost identical to the proof of the product rule. It just has a little twist in it that I really dig. So let's go ahead and do this. We're first going to state that f prime and g prime exist because they allowed us that within the theorem. And then logically from that, using just the definition of a derivative, the derivative of a function is just the function evaluated at x plus h minus the function evaluated at x all over h as h tends to 0. And that's what we wrote here. Now I'm going to steal a lot of the geometry I had from the product rule proof. So let me draw that down really quickly. From the product rule proof, we had this really cool idea that, oh, okay, I have this central, or I suppose this square right here. It's not central, but the lower left square. And I said the height of that square was the function value of f at x. So it's just some number, f at x. And then I said the horizontal distance, at least for the product rule, was g of x. However, in this case, we don't have f times g, we have f divided by g. So I'm going to call this horizontal distance a 1 over g of x. Now that's basically 1 over g of x, okay? But I'm just going to write it that way for now. And then we also noted that we wanted to increase these values. We want to wiggle these values a little bit. So we wanted to wiggle the outputs of f and that blue 1 over g. We wanted to wiggle those values. So to do that, we had a change in output for f. That was what this distance was. And we had a change in output for 1 over g in this case. It was g in the product rule case, but this is going to be our change in output for 1 over g. And we defined that change to be just the numerator of the difference quotient. And if you need a review of that, please go see the video on the product rule. So this is going to be, basically if you're changing outputs, you had your original output and you have your new output. The change in output's just a difference between those, right? Difference between new and old. That's what our change in f is going to be. Now, if somebody yells at me and says, how do you know that the change is positive? I don't. I'm just geometrically saying this is the size of it. It could be a negative size. Don't worry about that. That's not that big of a deal. Likewise, the change in 1 over g, let me put that in parentheses here, is going to be 1 over g evaluated at x plus h minus 1 over g evaluated at x. Now, before I continue, I'm just going to note that's the same thing as 1 over g of x plus h minus 1 over g of x. That's going to be critical for the rest of this proof, as I found when I was trying to scrawl out what this proof would look like. Let's talk about areas now, just like we did with the previous proof for the product rule. The area of this lower left triangle, or sorry, rectangle, this beast right here, that is just going to be the product of f and 1 over g. That is, that area is going to be f over g. That's what that area is. Yes, of x, but I'm not going to write that in there. And let's see, the area of the upper left square is going to be the height, which is change in f, times the width, which is 1 over g of x, or you know what? I'm going to write that as 1 over g of x. It's just, it's the same thing. So I'm just going to write it that way. Likewise, the lower right triangle has a height of f. Its width is change in 1 over g. And we already know what that is. I just don't have the room to write it there, so I just wrote it this way for now. And finally, in the upper right-hand square, I have a change in f as its height and a change in 1 over g as its width. There we go. I think that's pretty good. All right, let's see what we could do here. If we've already defined our change in a function to be the function evaluated at x plus h minus the function evaluated at x, then the change in f over g must be this numerator by our definition. So I'm going to go ahead, and this mimics the proof of the product rule. I'm just going to say that numerator can be simplified initially as the change in f over g by our definition. Remember, change in f is just the numerator of the difference quotient. And so this change in this function, that's a difference quotient we're looking at. Here's the numerator, and the function name itself is f over g, so we're going to call that the change in f over g. But conceptually, if this area in yellow, if that area is f over g, and we wiggle the inputs a little bit, we get a change in f over g. We get a change in our output. And that change in our output is going to be all this other remaining area. All of it. That's our change in, let me point an arrow at that. That's our change in f over g. Here is f over g, and that's our change in f over g. All of that blue area, not just that one spot, but all of this blue area that I've highlighted. So if the numerator of our limit is the change in f over g, and that's the same thing as that blue highlighted region, well, let's go ahead and copy all of that blue highlighted region in. That's the limit as h goes to 0 of a big old fraction over h. Let's see, we had a delta f times 1 over g of x. Let's see, what else do we have to tack on there? I'm going to take this one first. We have plus f times a change in 1 over g, which we wrote down below. We'll clean that up. And finally, the upper right-hand corner, we had a change in f times a change again in 1 over g. Sloppy notation, but it works for the time being. Now let's split this into 3 fractions. This is where the fun begins. So let's see, I'm going to go ahead and write this as the limit as h approaches 0, something over h. The something is going to be change in f over h times g. That's this first fraction over h. Plus limit as h goes to 0 of f of x times change in 1 over g. I haven't replaced that yet, all over h. And then finally, plus limit as h goes to 0 of that last stuff, change in f times change in 1 over g. And again, this is all over h. So I just split it into 3 fractions. Nothing big. Baby stepping my way through, that's all. And now I know what delta f is. It's actually the numerator of a difference quotient. So I'll trade that out. Let me go ahead and do that right now. And by the way, I should note this g of x does not have an h inside of it, so I can move that out into the front of this limit. I'm going to go ahead and do that. It's equal to 1 over g of x times the limit as h goes to 0. It's supposed to be an h. And delta f, remember, is f of x plus h minus f of x. And this is still sitting all over h. That should look strongly familiar to you. Not strangely, but strongly familiar. The second fraction. Again, there is a picture there that does not rely upon h, so I can factor that picture out. So I get this plus f of x times the limit as h goes to 0. That's supposed to be an h, but just got kind of weird. And now I have this fraction with an h in it. Let's go ahead and figure out what delta of 1 over g is. We wrote it over here. Delta, the change in 1 over g, is just 1 over g of x plus h minus 1 over g of x. And that's 1 over g of x plus h minus 1 over g of x. That's this picture right here. So I'm going to go ahead and replace that delta g with 1 over g of x plus h. Let me go ahead and start that. 1 over g of x plus h minus 1 over g of x. The fractions make this kind of weird, but it's totally doable. Finally, plus, I have a limit as h goes to 0 of delta f over h times the limit as h goes to 0 of delta 1 over g. I'll just write it that way. So I split that product up, and we'll see if this is legal. You don't know if it's legal until you actually evaluate it to find out if it becomes finite. If it doesn't become finite, then, well, by golly, it's not legal. All right. Let's start simplifying notation. This is 1 over g times this definitely right here. Let me highlight it in yellow. This right here is f prime, and we were told f prime exists, so I could just trade that out immediately for f prime. Plus f times, well, this right here, we're going to have to do some manipulations. So what I'm going to do is multiply both numerator and denominator by g of x times g of x plus h. When I do that, I get the following. Limit as h tends to 0 of g of x minus g of x plus h, just using our good old algebra we learned way back when, over h times g of x times g of x plus h. We'll deal with that in a moment. Let's see, plus that first product, or the first factor here, is written as f of x plus h minus f of x, and that's all over h. Hey, I know what that is. And then the second limit, so times the limit as h goes to 0, is, let's see, what was delta of 1 over g? Oh, there it is. It's 1 over g of x plus h minus 1 over g of x. All right, so far so good. That is actually not too terrible. All right, let's see what else we can do here. All right, so this is going to be f prime over g. I'll just write that. Plus, nope, not plus. What I'm going to do is factor a negative out of this numerator right here so that I can write it as g of x plus h minus g of x. So I'm going to factor out a negative. So minus f times the limit as h goes to 0 of g of x plus h minus g of x all over h times, and I'll factor off that other limit, h goes to 0, of 1 over g of x times g of x plus h. I just want to showcase what I did. I just split this fraction here into basically the numerator over h times 1 over g of x times g of x plus h. So that should be okay with you. Hopefully it is. I'm trying to erase there. Let's see what else we have. Oh, that next piece right there, that's just f prime. Yay, f prime times. Now, this is the same argument that we used with the product rule. Since f and g prime exist, then f and g are both not only differentiable, but continuous. So as an aside, g prime exists, implies g is continuous, implies limit as h goes to 0 of g of x plus h is going to be g of x. And so as h goes to 0, I can then say that this last piece, sorry, didn't mean to do that, is going to be 1 over g of x minus 1 over g of x. And that is just a number minus itself, so that's going to be 0. And now we're almost done. This is going to be f prime over g minus f, and this product right here is g prime, times, as h goes to 0, this will be 1 over g squared. This piece right here, sorry about that. It's g times g. And then plus f prime, again, times 0. So in the end, you get down to f prime over g minus f g prime over g squared. I can combine those two fractions by getting a common denominator, which is called g. So multiply that first fraction by g and you get the following: f prime g minus f g prime all over g squared. And we have proven the quotient rule. Q-E-D, quote demonstratum. So it has been demonstrated. Very, very nice, clean proof of it that I've never done, actually. So that was kind of fun.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at ease. Says, listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.